Hi, we're going to start lesson 3.3, which covers ground states and excited states of electrons. Before we start, let's review what a Bohr model is. A Bohr model is a display of what atoms look like and where electrons reside. And we know they reside in specific energy levels. There's 7 energy levels. Most of them don't get to all 7. But we can have anywhere between 1 to 7. If we're drawing the Bohr model for magnesium, what we would do is we would start by drawing a nucleus. The nucleus should have 12 protons because the atomic number is 12. The atomic mass is 24. So we take 24 minus 12. That also gives us 12 neutrons. Those two go in the middle. Magnesium is uncharged in this case, so the number of protons should equal the number of electrons. Positive charges should equal negative charges. That will bring us to an overall charge of 0. We can fit 2 electrons on the first energy level, and we space them out because they're both negatively charged. They're going to repel each other. They also want to be closest to the nucleus because they're attracted to those positive charges. We can fit 8 electrons on the second energy level. That brings us to 10, and then we can put our last 2 on the third energy level. Okay, if we notice, there's 3 energy levels in magnesium, and magnesium is in the third period of the periodic table. Period number equals the amount of energy levels we have. Again, this should feel like review. Right now we're going to talk about the idea of electron states, or states of the atom in which the electrons are sort of arranged. So if we're talking about an electron state or a state in general, this is the arrangement of electrons around an atom's nucleus. So in each of these energy levels, electrons are sort of in these not fixed positions, but like free-flowing areas where they're orbiting the nucleus. Now these states, why we're calling them states, is because they occur at a particular time. The first state that we're going to talk about is the ground state. And for lack of a better word, the ground state is sort of the normal display of electrons in their respective energy levels. So we've been drawing these Bohr models, and the way that we've been drawing them with 2 in the first energy level, 8 in the second, 8 in the third, this is kind of giving us an idea of what the ground state is. It actually is not giving us an idea. It is what the ground state is, like where they would occur naturally that requires the least amount of energy. We know that atoms have inherent energy, but ground state requires the least amount of energy. So when we calculate energy, if one energy is lower than another, we know that one is in, the lower one would be in the ground state. We've talked a little bit about movement between energy levels, and when this happens, we have something called the excited state. And the excited state is a temporary state in which electrons in a lower energy level can move to a higher energy level. Again, there's sort of like conditions to this that we want to be aware of. There's sort of 3 conditions. First condition is that each energy level must have at least 1 electron. So if we're moving electrons from the first energy level to the second energy level, we can only move 1 because we still need 1 in the first energy level. Number 2, we cannot exceed the maximum number of electrons in the energy level, or that fit in the energy level. So in the second energy level, we can only have 8. If there's already 8 in the second energy level, we can't add 9. There's not enough space to do that. And then number 3 goes back to definition and this word temporary. After electrons are excited, or when they move to a higher energy level, it's only temporary. Once that excitation or excitement is done, the electrons return to the ground state. Atoms are a part of nature. Nature likes when energy is low. Kind of the short answer to something a lot more complicated, but we don't need to get into that today. We'll get into that next lesson. There is 3 main ways that we can excite an electron. Well, there's actually 4, but 2 of them are kind of the same. But the ways to excite an electron, we should know one of them. First way is collisions with photons. So when light interacts with an atom, what it's doing is it's pushing electrons into an excited state. When you turn on a light, you're exciting all the electrons around you. That's why we see color. As soon as you turn the lights off, there's no color. As soon as there's no light, you might have a hard time seeing that. Second way, it's kind of combined with 2. When we have electric fields, we're constantly exciting electrons. This is more of a topic of physics. When we have electric fields or electric currents, things going on in light bulbs, those are all excitations of electrons. As soon as you turn on the light, you're exciting electrons to do all of their things that they need to do. And the last one, which is what we use primarily in chemistry and in this class, is heat. Heat. Anytime we heat something up, we're allowing electrons to do certain types of work. And we're going to do a whole lab on exciting electrons when we get back from Thanksgiving. How we can show electrons in the ground state and the excited state is actually really simple, and we're going to use the Bohr model to do this for now. once we have an idea of different types of orbitals, we can go into more detail about it. But for now, let's look at something like nitrogen. Nitrogen is atomic number 7, element symbol N, atomic mass is 14. The ground state is basically the Bohr models that we've been drawing up to this point. So we're going to put our protons and neutrons in the nucleus, and we're going to put our electrons in our respective energy levels. Nitrogen has 7 electrons, it's uncharged. If we put 2 on the first energy level and 5 on the second energy level, we have the ground state arrangement of electrons in nitrogen. If you notice on the ground state, there are some empty spaces on the second energy level where electrons can actually fit. So if nitrogen had a -1 charge, we could fit an electron here. If it had a -2 charge, we could fit an electron here. If it had a -3 charge, we can fit an electron here. This is an opportunity for us to actually excite the electrons. And what we mean by excite is we mean that I can take one of these electrons from the first energy level and put it into one of these empty spaces on the second energy level. Doesn't matter which one you decide to pull. You can pull the one on the top or the bottom. But the way that we show that we excited an electron, specifically for nitrogen, is we need to have 7 protons and 7 neutrons in the nucleus. That tells us that we're working with nitrogen. And instead of drawing 2 electrons on the first energy level, we're just going to draw 1 because the other one's going to go into the second energy level. And I'm going to pull the one on the bottom. And instead of having 5 on the second energy level, I'm now going to have 6. This is the temporary excited state for nitrogen. And as you can see, I pulled this from the first energy level and moved it to the second energy level. Cool. If you're working with one of the noble gases, and we can just use neon for this, neon is atomic number 10, it's Ne. Atomic mass is 21. As you can see, if we draw the ground state for neon, which again is just the Bohr model, I'm going to do exactly what I did for nitrogen, 10 protons, 11 neutrons. Make sure that my nucleus is clear. I'm going to draw 2 energy levels because I know there's 10 electrons. If we look at the ground state of neon, there's no room for us to move any of those electrons. There's no space on the second energy level. There's no way that we can excite these electrons. And you might think that you can just add another energy level, but that energy level doesn't exist. So for neon or all the noble gases, there's no excited state. Okay. Noble gases are a little bit weird. It basically relates to the idea of stability and reactivity. Last couple of things before we talk about atomic orbitals is during the movement of electrons, the emission of light changes. So basically, depending on how much how much energy is released. So if energy is released at a lower amount, the wavelength is going to be much higher. If the energy is released at a lower amount, if the energy is released at a higher amount, the wavelength is going to be lower. Okay? In a way, this is sort of explained by the Heisenberg uncertainty principle. You won't have to know how to do any calculations around this, but I think it's important for us to kind of get an idea of what Heisenberg kind of said. And he said, in very short terms, that you cannot know the exact position and momentum of a particle at the same time. Basically, when we're moving electrons, we don't know exactly which electron is moving from the lower energy level to the higher energy level. And his principle says delta x times delta p is greater than Planck's constant over 4 pi. Again, you don't need to know how to use this equation. All you need to know is that position and momentum cannot be determined at the exact same time. In other words, like I just said, when we're moving an electron from the lower energy level to the higher energy level, we're not exactly sure which of the 8 electrons on one energy level is moving. We just know that one is moving. And the Bohr model is actually a really nice way to kind of handle all of this. When we come back next time, we're actually going to talk about the idea of Erwin Schrödinger's atomic orbitals. So in conjunction with Bohr's energy levels, we also have this idea that within an energy level, there are orbitals or kind of specific paths that an electron takes to orbit the nucleus. And Schrödinger calculated this based on the amount of energy and attraction that goes on between the electrons and the protons. He also used quantum mechanics to kind of understand if there's a certain amount of energy already within the energy level, plus the attraction of the nucleus and the energy level, the electrons have to be moving in a certain shape, depending on where they are in the atom. So we're going to keep Bohr's idea of these energy levels, but we're also going to add something called an orbital. And these orbitals can hold a certain number of electrons. So in the first energy level, we have an s orbital, and that can hold 2 electrons. In the second energy level, we have what's called an s, well, we have, again, the s orbital and the p orbital. In the s orbital, we can fit 2 electrons. In the p orbital, we can fit 6 electrons. So that gives us a total of 8. Again, same idea. Now we're just in fixed paths. We're not just in the energy level. Within the energy level, there's specific paths that the electrons are taking. In the third energy level, we have an s orbital, a p orbital, and a d orbital. In the s orbital, we can fit 2 electrons. In the p orbital, we can fit 6 electrons. In the d orbital, we can fit 10. This is going to give us a total number of 18. And then in the 4th through 7th orbitals, we have, 4th to 7th energy levels, we have an s orbital, a p orbital, a d orbital, and an f orbital. In the s orbital, you can fit 2 electrons. P, you can fit 6. D, you can fit 10. And in the f orbital, you can fit 14. That gives us a total number of 32. Okay? When I break down these orbitals, I'm also going to give you the shape of them. So if we look at the orbital, the number of electrons it can hold, and the shape, they're all going to look a little bit different. The s orbital, again, can hold 2 electrons, and the shape around the nucleus, so the nucleus I'll draw in the middle, the shape is just a circle. The p orbital can hold 6 electrons. When that path around the nucleus occurs, we have sort of like an infinity sign or like a bow tie. So these electrons will follow this specific path. The d orbital can hold 10 around the nucleus. It looks like a 4-leaf clover or a butterfly of sorts. And in the f orbital, we can hold 14. The f orbital has 4 kind of flaps on one side and 4 flaps on the other side. There's 8 flaps total. We'll get into this a little bit more when we talk about electron configuration and how that sort of makes this a little bit easier, and we can use the periodic table to do that. So if we're looking at an element like ruthenium, we can actually use this knowledge to understand how many energy levels it has and what orbitals it would have. Ruthenium is atomic number 44, it's Ru, the mass is 101. If it has 44 protons, it also has 44 electrons. So if we start at the top, the first 2 electrons will be in the first energy level. That's going to take us to 42. So energy level 1, or energy level 1. After that, in the second energy level, we have an s and a p orbital, which takes us to 8. So that'll be 36. In the third energy level, we can fit 18, which gives us 18 left. And in the fourth energy level, we could take this, the fourth energy level can fit 32. So that means that we have 4 energy levels. In the first energy level, we have an s orbital. Second energy level, we have an s and a p orbital. Third, we have an s, p, and d. And in the fourth energy level, we have an s, p, d, and f orbital. Cool? Again, this should make a little bit more, I know I'm not here, so I will go over this the day that we get back from Thanksgiving because we have this class. I think this is a nice way to kind of introduce the flame test lab and get us ready for electron configuration. Remember that I did an uncharged element here. How would this change if it was charged? Meaning that we add protons or electrons to this. Cool. Thank you.